All right, so we've reviewed the exam, you've done the course evaluations. The one announcement that you should have on your radar for now is that the final homework assignment, homework 11, is due on Friday, the 4th of December by 12 noon. And then the final exam, I'll mention this in class on Thursday, but the final exam is Thursday, December 10th, from 10:15 a.m. to 12:15 p.m. And the format of that exam is going to be the same as the midterm exams, where you have a 2-hour window to access a PDF file on Blackboard. You can print it, or you can just work it on a separate piece of paper. Then you need to scan your work and upload it back to Blackboard before the 12:15 closing deadline. So we've been through it a couple of times already, and all of the same conditions will apply. The exam is cumulative, partly because it would be nearly impossible to give an exam that wasn't cumulative in this class, but there will be added emphasis on the material since the second midterm exam. And so now we're in Chapter 7, and you haven't had Chapter 7 covered in either of the previous midterm exams. And so proportionally more of the points will come from Chapter 7 material than otherwise would be the case. Just, it's only 3 lectures, but it'll be more than 3/28 of the exam. All right. So any questions on these announcements before we start continuing to talk about the energy equation from Chapter 7? All right. I sent out a PDF file shortly before class, and let me bring it up because we're going to take a moment to look at that together. All right. So here is what I normally conduct as a critical thinking activity when we meet together in person. It's a little more awkward to do it the way I normally do if we're meeting remotely, but just because it was a long vacation, see if you can, whether you're able to write the energy equation from memory in that box. And so remember, the energy equation is slightly different from the Bernoulli equation. There are some important additional terms that are on there, and then slight variations in the common terms between them. But what I'd like you to do is fill in the energy equation and then explain what are the differences between the left-hand side and the right-hand side of the equation. And let me pause for just a moment to see if you can puzzle out that from memory, and then we'll take a look together on some of the things I'm trying to get at in this activity. All right, so let me bring this up. Of course, the energy equation has, a little awkward there. All right. The energy equation has the pressure head term, the elevation head term, and the velocity head term. And the differences between that and the Bernoulli equation is that on the left-hand side we also have the pump head term, and what that accounts for is the energy that's added between location 1 and location 2. And remember that in this case water flows from 1 towards 2. And then on the right-hand side of the energy equation is a term that accounts for whether there's a turbine extracting energy from 1 to 2, and then also a combined head losses term. And you might have written that as local losses, H0, and the friction losses, HF, and that's fine. But HL collectively accounts for those two terms, the energy loss due to pipe friction and the energy loss due to local losses. So it's important when you're writing energy equation that you don't accidentally switch the pump and the turbine terms. The pump term belongs on the left, and the turbine and the losses term belongs on the right, because turbine and losses remove energy as the water's flowing from 1 to 2. All right, so the next thing that I asked you to consider is in this diagram, let's take a look at the water is going from the left to the right. We get that from the arrows. And the elevation of the tank on the left is 200 meters at that water surface elevation, and on the right-hand side it's 230 meters. So the water is in effect flowing uphill. And I ask you, this symbol, does that mean that it's a pump or a turbine? So anybody willing to venture a guess in the chat box there, or you could do the unthinkable and unmute your microphone. Anybody have a guess on whether this is a turbine or a pump?
My guess would be a pump.
You're right. What made you guess that?
The direction of the fluid, it's going uphill at a certain point.
Yep. Yeah, exactly. It wouldn't be able to go uphill unless something was adding energy. And so if the water's going from 1 to 2, what we know is that at the surface of the tank, it has no velocity and it has no pressure. And so the energy equation would say that, you know, the energy here at location 1 is just its elevation, z. And so the energy at 1 is 200 meters, and the energy at 2 is 230 meters. So let's look at how that would be possible. So you have to be adding energy through a pump to get 200 plus something is equal to all that there is on the right-hand side of the equation is the elevation at 2, which is 230. And so the way that we know it's a pump is that otherwise the water wouldn't be able to get lifted up to that greater elevation. And so it's a pump, and we can tell that just from the context. Okay, now in the figure, there's also this R to D ratio. And so notice at the elbow, it's mentioning what the R to D, it's equal to 1. And the students who were in the Civil Engineering 319 lab got kind of a sneak peek of what that might be related to. And so I'm hoping that maybe one of them would be willing to chime in on what is the significance, like why is it given this R to D? What do you think it stands for, like the R and the D? But maybe more importantly, why is that specified in this bend? So any civil engineering students who were in the lab 2 weeks ago willing to chime in and guess on what's going on at that elbow? Zach, any guess? Or Courtney? I know Courtney was in the lab. Jacob says, is that the K value? And the R to D is not the K value, but it is related to the K value, so you're definitely on the right track. Now, let me show you in this, the end of this file that I sent, there's a loss coefficients for various transitions and fittings. And so when the water goes around a bend like this, it's losing energy just because of the change in direction. And the sharper the transition, the more energy is going to be lost. And so the R here stands for radius, and that means the radius of curvature of the bend. And the D means diameter, meaning the diameter of the pipe. So what this is a reflection of is how gradual or how abrupt is the transition from horizontal flow to vertical flow. And now let's go back down to this table that I was showing a little bit earlier. And what this shows is K values. And K values are an indication of how much energy is lost at a fitting or a transition. And we'll, as I'll show you in just a moment, you multiply the K value by the velocity head at a certain location in order to calculate the head loss at that spot. But look at the really abrupt 90-degree miter bend has a K value of 1.1 if the veins, which would guide flow in there, don't exist. If those veins are inside the miter bend, then you can bring the K value down much lower, down to approximately 0.2. Okay, so this is an abrupt transition. If it's just two pipes with no radius of curvature, 1.1. But if you do have some curvature there, then the K value is lower. And depending on how gradual the transition is, the K value may decrease even further. And so you'll notice that the R to D of 2 has a K value of 0.19 instead of the K value of 0.35 if it's a 1. And so if it's 1, that would be a little bit of a gradual transition. But of course, there's a limit. If you get the radius to diameter much larger than 4, then the K value starts going back up again. And that's because it's now a really lengthy transition. And so it's redirecting the flow gradually, but you're adding length to the pipe. And so there's a little bit of friction loss that's going on there. So this table has information about a lot of different types of fittings, like different valves. A globe valve where the water is entering, changing direction, going through a restricted diameter opening, and then changing direction again. There's a really high K value there because there's a lot of energy loss as water goes through a globe valve. In comparison to that, a gate valve that's fully open has hardly any energy loss, it has a low K value. And so this table can be used to estimate the effects of local losses. So in this figure, the elbow radius to diameter is given specifically so that we could account for the local losses that occur. Of course, there's energy being lost as water goes through the pipe, and that's a distributed loss. But there's also what's sometimes called a minor loss, but maybe the better word for it is a local loss, when water has this localized turbulence caused by a valve, a fitting, or a change in direction. So what are the other two locations where localized energy losses could occur in this diagram? So the other two locations is the inlet and the outlet. And let me go back to the table and show you how we handle inlets and outlets. Those are considered as a pipe entrance where you have a really large diameter pipe going to a small diameter pipe. I guess maybe the expansion, expansion and contraction. So when the water is entering a pipe, we use a K value of 0.5. And so when the water is coming in, there's some losses associated with a stationary water beginning to accelerate and enter that pipe. And then at the outlet, it's losing all of the velocity head, and so the K value is 1.0. So on the table here, an infinitely large expansion, the D1 to D2 of 0 gives you a K value of 1. And so if you've got this printed out, just maybe put a star next to that, but that's an outlet. And then the inlet, a pipe entrance where you have a radius of curvature of 0, it's 0.5 for the inlet. Now those K values, I'll show you in just a moment how you apply those in the energy equation. But besides fitting, energy is lost as water flows through the pipe. Identify 3 factors that you think could influence the rate of energy loss through the pipe. So water's flowing through this pipe, and some of the factors that determines how quickly energy is lost through the pipe could be like the pipe material and whether it's a smooth or a rough material. And so if it's, for example, like a rough finished concrete, then you're going to be losing energy at a much faster rate than if it was a drawn glass tubing that's very smooth at the boundary. Okay, so pipe material and roughness would be one factor. Another factor is the diameter of the pipe. So a large diameter pipe is going to have less energy loss than a small diameter pipe. And related to that is the velocity of flow through the pipe. So those are some factors that can influence the rate of energy loss through the pipe. Okay, so we did some problems related to this on the Thursday before Thanksgiving, but let me pause for a second and see if you kind of remember how to fit this all together. Now, I mentioned that I was going to show you how you deal with the K values, and what you do is the local losses, you add up all of the K values together, and then you multiply that by the velocity head, v squared divided by 2g. And so remember, for this r to d of 1, let's go and refresh our memory on what's the k value there. So r to d of 1, that k value is 0.35. And then we have, okay, so 0.35 here, 0.5 there, and 1.0. So 1.5 and 0.35, that's 1.85 is the sum of the k values. Now, this equation is called the Darcy-Weissbach equation. And this formula is a way of estimating the amount of energy loss due to pipe friction. And so we can see that this particular pipe has a given F value of 0.015. And this is an indicator of the roughness of the pipe. And so the Darcy-Weissbach equation has that term F that accounts for how rough it is. It also has the length of the pipe being accounted for. And so overall, it's 1,000 meters of pipe length. We're solving for an unknown velocity. And so here in the Darcy-Weissbach equation, V is the unknown. We do know the diameter, and of course we do know G. So what you should do is use the energy equation, which we saw here. So use the energy equation, and HL is H naught plus HF. So 200 is the Z1, 230 is Z2. Location 1 has no pressure because it is at the top of the reservoir where the air is touching the water. There's no pressure at location 2. There's no velocity at 1 or 2, but there is a velocity in the pipe. So let me pause for just a second and give you a chance to try and solve for the V. What is the velocity of flow? And then you can determine, once you know the velocity and the pipe diameter, you can get the flow rate. So start setting this up, beginning with the energy equation. So up on screen, we are kind of applying the energy equation to this given situation. And you can see that we're saying location 1 is at the top of the left tank, location 2 is at the top of the right tank. And so what we know about those locations is that there's no pressure and no elevation, but at each of them there is an elevation. So 200 on the left, 230 on the right. There is a pump that's adding energy, and in the problem statement it says that the pump is adding 40 meters of head. It has to add at least 30 meters or else the water isn't going to flow from left to right. So 30 meters and we'd have essentially zero flow rate. But anything beyond 30 meters of head, and that's going to cause water to start trickling through this pipe. And the higher the pump head is, the faster the water is going to flow because there will be more of a driving force causing it to overcome pipe friction. Okay, so I've canceled out the terms that don't apply. There's no turbine, but there is both friction losses and local losses. All right, so substituting in the given information that we've got the elevation on the left, the 40 meters of pump head that's added, and then on the right it's 230 meters, and then the expression for the friction losses and the expression for the local losses. And V, the velocity in the pipe, is unknown for both of them. And now don't get confused because we canceled out the V term there and we canceled out the V term there. That doesn't mean that you cancel it out in the loss equations, because V1 just means the velocity right at a point, whereas the velocity that goes into the Darcy-Weissbach equation and the equation for local losses, that V is talking about the velocity as the water is moving through the pipe. And that's not zero. That's what we're trying to find, is the velocity of flow and therefore also the flow rate. Okay, so what we have is a 10-meter elevation and pump head differential that's driving the flow. The reason why the water is going from 1 towards 2 is because there's more energy on the left than there is on the right. So the water is going from a location of high energy towards a location of low energy. And you can see that of these two factors, of the friction losses and the local losses, by far the more significant of the two is the friction losses. So look at the magnitude of that coefficient in front of the v squared term. So 1.9 is the combined effect of the friction losses compared to 0.09 for the local. So, local losses are sometimes called minor losses for the simple fact that they don't contribute, in most cases, that much to the losses. When you take like a long distributed pipeline loss into account, the fittings and the valves are in some cases negligible. And it depends on how long the pipe is and how fast the water velocity is, but the local losses are usually less important than the friction losses. So you can see what I've done is solved for the V, and so that means the velocity through the pipe, and it's 2.23 meters per second, and then if you multiply that by the cross-sectional area of the pipe, that's where we get the flow rate of 0.281 cubic meters per second. So there undoubtedly will be some kind of problem on the final exam that looks like this. I haven't written the final exam yet, but there almost always is some kind of a problem like this where you're having to account for both local losses and friction losses, and you'll be given some certain amount of pump head and then determining what's the resulting flow rate that can occur. And so if you found, for example, if this is a real world scenario and you're trying to get water up to this elevated tank more quickly than 0.281 cubic meters per second, then what that would tell you is you need to add more pump head. So you need a bigger pump that's able to add more than 40 meters of head. And so if you're adding 50 meters of head, then that would essentially double the driving force that's available to overcome friction and local losses. And so that would increase the flow rate a lot. It wouldn't double the flow rate because it's a nonlinear relationship. But all right, so any questions on this example? Okay, so that is how the local losses and the friction losses can be combined into the same equation to determine an unknown flow rate if you do know the pump head that's being added. Now, on the subject of pumps and turbines, sometimes we need to translate a given head value, which has units of length, into power. And power is going to have units of watts. And so the way it fits together is, let's take, for example, the case of a turbine, where we have some elevated reservoir and the water is flowing down through a pipe. In the case of a reservoir, those big pipes that carries water towards the turbine is called a penstock. An elevated reservoir is exchanging potential energy for electrical energy. And let's just take a look at what if we knew the elevation of both the upper and the lower reservoir. And so you can see that both of those are given in this example. And we know how much energy loss the fluid experiences as it goes through this conduit. Maybe we have an idea of the roughness of the material that's used in the conduit, its diameter, and the flow velocity. So we've separately calculated the amount of head loss that's going to occur. And we know the diameter of the penstock and the flow velocity. So the power equation that tells you the amount of watts that can be harnessed by this turbine, the power equation is the flow rate multiplied by the unit weight of the fluid and then the turbine head that's being extracted from the system. So if we want to find out how much electricity this turbine is capable of generating, then what we need to do is substitute all of this into the energy equation and solve for H sub t. And then once you have H sub t, you can substitute that into the power equation. At a start, let's just assume 100% efficiency. And that's what this equation, as it's written here, presumes, is that the system is 100% efficient at turning a turbine head into electrical power. In part B, you can see that we're also going to consider what if it's 70% efficient. But as a starting point, let's begin with 100% efficiency, and then when you get on to the second part where we're saying what if it's just 70% efficient, then since this is a turbine, what we'll do is we will multiply the power that we calculate can be generated by the efficiency factor as a decimal, and then that would tell you the amount of power that can actually be generated at that lower efficiency. Okay, but this example starts with the energy equation. And so let me carry that over from a previous, here it was. Let me paste it into this example so it's just right there in front of us. This is maybe one that I would write on the board if we were together today. All right. There it fits. All right. So let me pause for a second. Location 1 is the upper reservoir. Location 2 is the lower reservoir. So I think that gives you a hint on what to do with the pressure at 1 and the velocity at 1. What won't cancel out is the z values. But solve for h sub t, and then once you have h sub t, substitute that into this power equation. Okay, I'll pause for a moment and then I'll rejoin and we'll go through this together. Okay, so we have this elevated reservoir and water is flowing through a pipe to the lower reservoir, and with the energy equation what we're trying to do is determine the turbine head that can be extracted. So here is the full version of the energy equation, and what we know is that since we're working from the reservoir on the left at the surface of the water, it has no pressure and no velocity, and the same thing is true at location 2, then both the pressure head term and the velocity head term on the left and on the right cancels out to 0. So the turbine head is just going to be, and also there's no pump. So the turbine head, how much energy can be extracted from the turbine is the elevation difference minus the head losses that occur. And so I've substituted into the energy equation, and what we see is that you can extract 127.1 meters of energy with that turbine. That's how much of the elevation difference remains to go into the turbine, because we have to subtract out the pipe losses, the 5.4 meters of head loss that occurs through the penstock. That reduces how much energy is available to go into the turbine. Okay, so now if we know h sub t is 127.1, then the next thing we have to have is the flow rate. And of course you can get the flow rate in volumetric terms because the average velocity is known, 2.4 meters per second. And then from the diameter of that pipe, you can calculate the cross-sectional area. So Q equals A times V. So you get Q, and then since this is water, we know the unit weight is 9810 newtons per meter cubed, since we're working in SI units. So here's the power equation. Get the volumetric flow rate of 4.24 cubic meters per second. And then if it's 100% efficiency, then that means that we can generate 5 megawatts, 5.3 megawatts. So 5.29 times 10 to the 6th watts. And that's a really high flow rate and a really large elevation difference that's contributing to a pretty large pump head. And so this is an enormous amount of power that can be generated with that much water flowing that much of a vertical elevation difference. So the power equation at 100% efficiency, but now think, if it's only 70% efficient, then that means that less power can be extracted for electricity. I mean, more of the energy is going to go into things like losses, vibrational losses, heating losses that occur inside of the turbine. And so if it's 70% efficient, then we'd take that 5.29 times 10 to the 6th watts and multiply it by 0.70. And if it's 70% efficient, then it would be 3.7 times 10 to the 6th watts. Okay, so are there any questions on how to determine the power that's being generated in a case like this? Any questions from this example? Okay. Now, a little bit more about the local losses. So you can see this is a schematic that's showing the streamlines that would occur inside of a pipe that's changing direction. And as the water goes around a bend, there's a separation zone on the inside of a pipe bend. And this is kind of like a cross velocity where because of the change in direction and contact with the pipe wall, it actually causes some of the flow to go opposite to the bulk flow, and that reduces the effective area that the water is able to flow through. So instead of having a pipe diameter determined by the actual physical size of the pipe, the effective flow diameter is decreased. And so as the water's having to squeeze through a smaller area, because of that acceleration that occurs, there's a reduction in the pressure and therefore a local loss. So you could calculate that K value that applies by measuring the pressure change that occurs between the inlet and the outlet to a fitting like this. And experimentally, that's what we did in the lab a couple of weeks ago, is we looked at a variety of different fittings, and we were trying to determine what was the K value that applied by measuring the pressure change upstream versus downstream from that fitting. So you can apply all of the K values together, adding them up, multiply it by the velocity head, and that's how you determine these local losses. And we've already looked at the table that has, for a variety of different pipe diameter changes. And so think about, if you have a small pipe going into a large pipe, the K value depends on how big of a difference in diameter you have between the inlet and the outlet. And so the closer together that those two are, so you notice this D1 divided by D2 ratio of 0.8, that's saying that the inlet diameter is 80% of the diameter of the outlet. So there isn't much of a change in diameter, so the velocity isn't experiencing much of a change either. And so the K value is much smaller, meaning that there's less of an energy loss than if you have a more dramatic increase in diameter. The other factor that's shown in this table is that whether it's an abrupt transition or a tapered transition has an effect. And so you'll notice this angle, theta. They're saying that if you have a 20-degree transition angle between the inlet and the outlet diameter, then the K values are lower than if that angle is 180 degrees and it's an immediate small pipe, instantaneously a big pipe without a gradual expansion. And so a higher K value is associated with more abrupt transitions. And so the more gradual and the less dramatic the change in diameter, or the less dramatic the change in flow direction, then the K values will be smaller in those less dramatic cases. Energy is lost in an expansion for some of the same reasons that occurs when there is a change in direction. So you can see a zone of separation where effectively, although the pipe diameter has increased, there is this location where the water is swirling around. There's an eddy, and counter flow velocity that effectively decreases the flow diameter, and it is in some ways causing more of a loss than if it was just contact with a stationary pipe, because you actually have water that's going the opposite direction, and so there's a shear stress that's applied to the fluid that's coming through in the direction of flow. The shear stress of having a fluid that's going the opposite direction is greater than if it was up against a stationary unmoving surface. And so one of the ways to calculate the energy loss in an expansion is to look at the difference in velocity between the inlet and the outlet. And so here you can see this simplified approach to calculating what would be the head loss that occurs in an expansion. And if water is flowing into a reservoir, then what's lost is the entirety of the velocity head. So if you have water that's moving in a pipe, it has velocity head, and suddenly it discharges into a tank, then there isn't going to be any remaining velocity head when the water goes into that stationary water inside of the tank. Okay. In the homework assignment, I got to refresh my memory of whether this is a homework problem that you still have on your upcoming assignment. Let me just pull open the homework that you have on your plate right now. Okay, so your homework 11 is the one that you're going to be turning in on Friday. And no, I've made some changes to that assignment. So this slide does not apply. That is before I fixed the problem. The problem used to be more confusing than it is now. Let me bring it up since I mentioned it. So this is what your homework assignment looks like. This is the one that's due on Friday. And what you're going to be doing in this second problem is you're going to be determining the velocity in the pipe, because you know the elevation difference between the water tank surface and the outlet. When the water comes out of this pipe, it still has its velocity head. And so that's one point that I wanted to make for you, is that you're going to be using the energy equation here, and I tell you how much pipe friction loss there is. I say for every meter of pipe length you have 0.152 meters of head that's lost on the basis of pipe friction. In this particular second problem, you're neglecting the local losses, but you need to set the energy equation to where 1 will be at the top of the water surface, 2 will be at the outlet in that jet. But remember that when water comes out of a pipe, it no longer has pressure, but it will still have velocity head. So you're going to be doing the energy equation from 1 to 2. Now just looking at it by inspection, you can tell that there's no pump and there's no turbine, and so those terms will drop out of the energy equation, but there are losses. But applying the equation between 1 and 2, you do need to leave the velocity head once the water discharges out into the open, but there is no longer pressure in the jet. But then when you go back between this outlet and location T, the water will have pressure, because location T is where the flow is still inside the pipe. Okay, so with that hint, that is it for today. This one no longer applies. Let's take a look at the announcements before we go our separate ways. All right, so homework 11 is due by 12 o'clock on Friday. Our final exam is on Thursday the 10th. And then if you have any questions about your test or how it was graded, then feel free to send me an email or give me a call on Teams, and I'll be glad to go over it with you. All right, well, that's it for today. Hope everybody's doing well, and I will see you again on Thursday. Take care, everybody.